Hello, my name is Rosa at Medina, and I am doing a presentation on enzyme kinetics with the Michaelis Menten model. So, enzymes are special proteins that can be thought of as catalysts because they help speed up or initiate reactions, but they are also regulators. They may perform the reaction itself, guide it, or modify substances so that they can participate in the next phase. Normally, reactions would take longer to occur because the reactants have to run into each other by chance in the correct position as well. As you can observe in the bottom picture, the enzyme performs this pairing and positioning task for them, so you don't have to do it and rely solely on chance. Other times, as seen at the picture above, they break apart or modify the substrate. But enzymes have so many different purposes that it's hard to define their mechanisms in just one way, which is why this general model is a very good place to start. The Michaelis Menten model allows us to observe how the initial velocity of a reaction changes based on the substrate concentration. K-on is the rate constant of when an enzyme E and a substrate S associate to make an enzyme substrate complex, which is represented by ES. They're literally just like stuck together. K-cat is a constant when an enzyme complex dissociates to form a product P and a free enzyme once again. K-off is a constant of when an enzyme complex dissociates back into a substrate and an enzyme. This may seem odd and counterproductive, but why this happens is because a complex had no success in producing a product, so it releases the substrate so it can try again with a new one. In some papers in the National Library of Medicine, they refer to the constants differently, which is what I put there in parentheses, but I think that these non-number labels make more sense. K-cat you can think of as a constant of catalyzation. K-on you can think of as a substrate on the enzyme. And K-off you can think of it as a substrate off of the enzyme. It makes more sense. Okay, so Briggs-Haldane differential equations. Well, he is helping derive this Michaelis-Menten kinetics. So the one on the top left represents the rate of change of the concentration of substrate. As mentioned before, K-on is the association constant for the substrate and enzyme binding to form an enzyme substrate complex. So it makes sense that it is being multiplied times the concentration of the substrate and enzyme, therefore representing the proportion of enzyme and substrate that become a complex in 1 unit of time. Since we want to know the rate of change of the concentration of free substrate, we are subtracting the rate of the enzymes and substrates that become complexes. On the other hand, K-off is the dissociation constant of the enzyme substrate complex, so it makes sense that it is being multiplied by the concentration of enzyme and substrate complexes. That way, it is representing the proportion of enzyme substrate complexes that break apart to form free substrate and enzyme in 1 unit of time, and for that reason, it is added, because it is increasing the amount of free substrate. The one on the top right represents the rate of change of the concentration of a product. As you may remember, K-cat is the dissociation constant for the enzyme substrate complex when it breaks up into a product and a free enzyme. Once the substrate is transformed into a product, it can't go back. At least it is very uncommon, and the only thing that can produce substrate is the enzyme substrate complex, hence why the rate of the concentration of the product only has one factor. The bottom left equation represents the rate of change of the concentration of free enzymes. This is very similar to the equation above it because the formation of enzyme substrate complexes also decreases the amount of free enzymes and substrates. In this case, we only care about what decreases the amount of free enzymes. Although the dissociation of any type produces free enzymes, which is why we are multiplying the concentration of enzyme substrate complexes times the constants when it breaks up into substrate and enzyme or when it breaks up into product and enzyme. The bottom right equation represents the rate of change of the concentration of enzyme substrate complexes, which is why we are adding the rate in which the enzyme substrate complexes form and subtracting the rate in which the enzyme substrate complex breaks up into either substrate and enzyme or product and enzyme. It is the opposite of the equation to the left. So the first assumption that we are making in this model is that we have a closed system, meaning that no enzymes or substrates are being added. We are also assuming that the dissociation of enzyme substrate into product is the only thing affecting the initial velocity due to the steady state approximation, which just means that equilibrium was reached so rapidly due to high substrate concentrations that the amount of enzyme complexes disbanded is equal to those formed. So the only thing affecting the reaction rate truly is the rate the enzyme substrate complexes dissociate into a product. And lastly, we are also assuming that the only factors in this model are the interactions between enzymes and substrates. Only those two things are interacting and causing this sort of like change in product concentrations or reaction rates. So how does this all fit in with the Michaelis Menten equation? So the rate of the concentration of enzyme substrate complexes is assumed to be zero due to our steady state approximation, which makes sense. If we are at equilibrium and the concentration of enzyme complexes doesn't change, then there is no change, so it is zero. We only focus on the initial velocity of the reaction because trying to represent the velocity of the reaction at any point in time would be much harder. Thanks to these assumptions and conditions, we can set the differential equation of the concentration of the enzyme substrate complex to zero and solve for kcat times ES, which is just the product rate, or the rate that product is made. Notice, we can substitute ES with E total minus enzyme substrate complex, since we know that that would equal the amount of free enzymes. And in the end, it gives us this neat equation. Notice, we know that the initial velocity is equal to the rate in which a given concentration of enzyme substrate complexes become products. We also know that we reach Vmax when all the enzymes are already being occupied by a substrate, meaning that they are all enzyme substrate complexes. This is why we replace the concentration of enzyme substrate complexes with the total concentration of enzymes. Km is just a constant made up of proportions of those three constants, and that also happens to represent the concentration at which half the maximum initial velocity is reached. So if you think about it, you can verify this equation by finding the limit as the substrate concentration reaches infinity. And by using L'Hopital's rule, you'll find that it equals Vmax. And the reason behind this is because at high levels of substrate concentration, the enzymes will all be occupied, so the initial velocity of the reaction cannot go any higher. While at lower concentrations, you can notice that the initial velocity of the reaction increases as the concentration increases because more substrates are pairing up with the free enzymes. Maybe, like me, you think that if we found the integral of those differential equations, we can assume that it equals the concentration of the substrate or product at a given time, even though the units check out and end up giving you a value with the concentration unit. But take into account that if we did that, we would be assuming that the initial velocity of the reaction is remaining constant, but we know that that is not true. So something else must be done to model the concentration of the species. We'd have to create a dynamic model. First and foremost, S inner represents the amount of substrate at a given time towards the beginning of the reaction, while S outer represents the amount of substrate at a given time towards the later part of the reaction. They would have to make different assumptions and rescale the units of the variables, but you can sort of see the echo of the Michaelis Menten model when the derivative of this new model is taken. I attempted to find the derivative of S outer to see how it all fits in, though I was unable to successfully derive it. But I assume that because this is from an academic paper, their conclusion is most likely correct. You can see that initially there is a very high concentration of substrate, and over a short time, the early phase, the amount of enzyme substrate complexes peaks because the enzymes rapidly bind to the free substrates. As the substrate becomes part of the substrate complex and then a product, the substrate concentration decreases. Similarly, as the enzyme substrate complexes start dissociating into product and free enzyme, their concentration decreases as well. Notice how that early phase of pairing of the enzymes with the substrate occurs so quickly relative to the time of the rest of the reaction. That is why we can assume that the initial velocity mostly relies on the change of product concentration, though in some other academic papers they refer to the velocity of the reaction in terms of the substrate consumption rather than product creation, which makes sense. The rate reactants are consumed can help measure the rate of the reaction just as well as the rate the products are made. The velocity of the reaction, as seen previously, is not constant. Therefore, it would be hard to represent the dependence on concentration in addition to time. So we only focus on initial velocity. That is one of the many things this fails for. Furthermore, a very important assumption in this model we also made is that we are working in a closed system, and therefore we aren't accounting for the presence of inhibitors or molecules that may hinder the reaction or promote it. We are also not accounting for the production of new enzymes and substrates by the cell, or even death of enzymes, since they have a short lifespan. Though this is a more long-term thing, so since we're only working with initial velocity, it's not really that relevant. Okay, so since enzymes are regulators, they also have their own ways of slowing or starting the reaction if needed. Sometimes a molecule must turn on the enzyme, that's called a cofactor. Other times, the product itself may slow the reaction, that is feedback inhibition, because if there's a lot of product, it doesn't need to make more. Or in some odd cases, the presence of too much substrate may cause the reaction to stop, and that's substrate inhibition. None of these factors are taken into account. Lastly, if you remember at the beginning of the presentation, not all enzymes have just one binding site for a substrate. Some have multiple since they carry out different types of reactions, so this equation doesn't account for this either. But this doesn't really mean that this is not a really useful model. Despite these limitations, there are a lot of models that are rooted from this general model. Take, for instance, the one used to represent the initial velocity of the reaction, but taken into account substrate inhibition. The other takes into account multiple binding sites, and the last one takes into account the production of substrate. And R, the variable there, or R represents a certain equation that accounts for that. So yeah, it is a really good place to start and a good something to expand on. And here are my sources.